This video is going to be on improper integrals. Specifically, we're going to talk about three main points. First of all, what is an improper integral? Second, how do we actually integrate improper integrals? And number three, we want to go through some examples demonstrating how to. So first of all, what is an improper integral? And the basic definition is something that involves infinity. It's integrals that involve infinity. Here's our sign for infinity. Now there's two ways we can see that in an integral. Number one says the integration limits might have infinity as a notation. So here we have an example. I'm integrating 1 over x, but I'm integrating it from 1 to infinity. Number two is a different kind of idea. It says the integrand, we have an integrand that is unbounded. So here I have that same integrand, 1 over x, but this time I'm integrating from 0 to 1. Now I'm not going to infinity in my limits of integration, but if you look at how I would evaluate 1 over x at 0, that's infinity. So if I were to draw that function, 1 over x looks something like that. So from the integral from 0 to 1, I'm talking about this space here, and as I get closer to 0, that height is going to go to infinity. That's the two different ways we can have infinity involved in our integrals, either by the integration limits or just the integrand itself is unbounded at some point in between the integration limits. So if it involves infinity, how do we actually integrate this thing? And so our basic approach is to replace our problem point with some value a, some letter a, and then take the limit as that a either approaches the problem point or approaches infinity. So we're basically replacing our problem point with a variable and setting that variable to infinity with a limit. Now there's two different results that happen when we do that. If we write our problem in terms of a limit and that limit goes to infinity, what we say is the integral diverges. We can't find some nice solution to that integral. It diverges. On the other hand, if the limit is finite, so I take the limit and it ends up to be 2, then the integral will have some value, whatever that limit is. And we can say the integral is then equal to that value. Formally, I could write this out like this. Here's an integral where I have some function, and this is the case where the infinity is in my limits of integration. I'm integrating from some number a, whatever that is, to infinity. What I'm going to do is I'm going to write this as a limit. So I'm going to take the limit as b goes to infinity of the integral from a to b of the function. So I've replaced my problem point, that infinity, with some variable b, and I'm looking at the limit of this integral as b goes to infinity. Next, what I'm going to do is I'm going to evaluate that integral. So now it's just a normal integral that I've seen before. I'm going to find the solution, find the antiderivative. I'm going to take that antiderivative and evaluate it at my limits. So now I have this expression. And now I go ahead and take that limit. As I mentioned before, if that limit is infinite, then I would say that that integral diverges. I can't find that nice solution. If, on the other hand, if that limit is equal to some number, I would say the integral is equal to that number. Now let's go through some quick examples. In both cases here, I have the integral of 1 over x squared. And I'm going to try this two different ways. One where I'm looking at my problem point being in the limit of integration. So for instance, I'm going from 1 to infinity in the first case. In the second one, 0 is included as the limit of integration. And so 0 means that integrand will be unbounded at that point. So for the first one, I'll rewrite this as the limit as a goes to infinity of the integral from 1 to a of 1 over x squared dx. So I just replace the infinity sign there with the parameter a. I'm looking at the limit as a goes to infinity. But now I can actually do that integral. The integral of 1 over x squared is just a negative 1 over x. So this is the limit as a goes to infinity of negative 1 over x from 1 to a, which is the limit as a goes to infinity of negative 1 over a minus a negative 1 over 1. So now I've evaluated that a and the 1. So when I look at this, the limit as a goes to infinity of 1 over a is going to be 0. So when I'm actually evaluating this limit now, the limit as a goes to infinity here is 0. If my denominator gets really big, that term is going to go to 0. The limit of the other stuff is just a constant. So here I have minus a negative 1, so my solution here is going to be 1. So the integral from 1 to infinity of 1 over x squared dx is equal to 1. So even though I'm integrating out to infinity, I still get this nice finite solution equal to 1 in this case. Now look at the second case, I'm going to follow those same steps. Now here my problem point is at 0, so I'm going to limit as a goes to 0 of the integral a to 1, 1 over x squared dx. Once again, I'm going to do the integration and evaluate it at those limit points. And so just as I did before, I'm going to get a negative 1 over a minus a negative 1 over 1, so plus 1. But here we have a problem. Now when I evaluate this limit, I look at the limit, that first term, that negative 1 over a. 1 over a as a goes to 0 will go to infinity. So what this will result in is a negative infinity. And notice the little abusive notation here. I'm saying this is equal to a negative infinity. I really want to write that down as an equality. I'm just saying this is where it's going to negative infinity. And so what I would say now is the integral from 0 to 1 of 1 over x squared dx diverges. It doesn't converge to a nice solution as the first case did of equal to 1, so I just say that integral diverges because one of my terms there went to infinity. So I can check my work in Mathematica, and so I'm going to enter in that integral, so it'll be the integral, and from 1 to infinity, to get the infinity symbol, I use escape, INF and escape. My integrand is 1 over x squared. When I evaluate that, sure enough, I do get an answer of 1, which confirms what I found earlier. Now, if I change those integration limits to 0 to 1, Mathematica will tell me that that integral does not converge on that interval. So it's confirmed the response of the solutions that I found out. So that concludes these example problems, and it concludes this video on improper integrals.